All right, for our last things that we're going to do for calculus is we're going to prove some formulas from geometry using calculus. Things that you've been told, but nobody has ever given you any justification for. For example, volume of a cylinder is pi r squared h, volume of a cone, volume of a sphere. Those things were never proven, they were just stated. So you have the capacity to prove them now. So if we want to do volume of a cylinder, basically what we can do for a cylinder, cone, and sphere, and these are the ones we're going to do, is we can treat them as solids of rotation. So if I want to create a cylinder, I can just create a region in the first quadrant, and it will be a rectangular region. So one of the things you've got to watch for is we're not going to give any numerical values to anything. We want to prove a formula that has some variables in it. So but the variables are constant with respect to a given problem. So they're really variables representing constants. So those would be the radius and height of the cylinder. And that way when we do a rotation, we're going to see something like this, and we're going to get a nice cylinder. My drawing skills have not improved over the break. So, there's going to be your cylinder. So basically what you're going to do is a volume of rotation. So you have to remember the formula for volume of rotation is volume is equal to pi integral from a to b of f of x squared dx. All right. So we have to determine, what is a function that describes this? Well, our upper function here, f of x, is just f of x equals the constant radius r. So we're going to, and also, what are our limits of integration? Our limits of integration, we are going from 0 on the x-axis to h on the x-axis. All right, so this is our a and our b. So we can say that the volume is equal to pi times the integral from a to b is going to be 0 to h. Our f of x is just going to be r, so r squared dx. Now, one of the temptations you have to resist is this integral is not r cubed over 3. R squared is a constant. So this is the integral of 4. So the integral of 4 is 4x. The integral of r squared is r squared x dx. So this is equal to pi times the evaluation of r squared x from 0 to h. There are ways you can shortcut this as well, but I think it's fine to write this out like this. Then, because there's very little to it, because then it equals pi times, we plug in the h and we get r squared h, we plug in the 0 and we get r squared times 0. So this is equal to pi r squared h, and there you go, we've proved the volume of a cylinder. Woo! Okay, now let's prove the volume of a cone. All right, so volume of a cone is 1/3 pi r squared h. So you have various ways you can set up the solid of rotation. So one way you could set up the cone is like this. I was tempted to do that sort of by analogy to my to what I did with a cylinder. The problem is that you end up with this function, f of x equals r minus r over hx, and then you have to square that, and it's terrible. So we're not going to do that. So this turns out to be not a good setup. But when you go to your project, you might say, maybe I'll try setting up one way, maybe I'll try setting it up another way, maybe there's easier ways depending on how you set it up. So it's not always going to be the same amount of work, even though I'm setting up the exact same solid. So you set it up this way so that the cone passes through the origin, and then your function is simpler. So this function is y equals r over hx. So that, the clear difference is that this one has a non-zero y-intercept, and that throws a real monkey wrench in it. It's not impossible, by the way. It works. It comes out right. It's just extra steps. So if we do it this way, there's no y-intercept, and the function you're integrating becomes simpler. So then we have the volume is equal to, we should put on here, some constants. This distance here is going to be the height of the cone, and this value up here is going to be the radius of the cone. And I'm going to rotate it around. I kind of put my function in the way, but I'm going to rotate it around like that, and it's going to be a nice little cone. There's my nice little cone. I am a cone. A cone head. All right. So, and then I'll move this over here. So when we say volume equals pi times integral from a to b of f of x squared dx, then that's pi integral. So my a to b are still 0 to h, 0 to h, 0 to h. But my function a little bit more complicated here, r over h x, and I have to square that whole function, and then it's dx. All right, so there are various ways you can approach this integral. Remembering that the r and the h are constants, though, you can pull them out, and I decided that was sort of the best way to approach this. The volume then is pi r squared over h squared. We can put the pi in the top if we want, it doesn't matter. Times the integral from 0 to h of x squared dx. So that way I've just taken everything that's constant and factored it out. We could have done that with a cylinder as well and had just 1 in here, but I'm not sure that saved any work. Here I think it saves some work. So then I have, let's write this as pi r squared over h squared. I have the evaluation of x cubed over 3 from 0 to h. So I have pi r squared over h squared times h cubed over 3. So I'm being careful to write everything out, even though some of these steps are obvious. We'll see why in a minute. And then so that equals pi r squared over h squared times h cubed over 3. I can reduce the h's and I get 1/3 pi r squared h, which is exactly what we've always been told that that volume should be. Okay, so that's volume of a cone. So how about the volume of a sphere? Well, I tell you what, you do it. Mini project. So this is your mini project, and it is really super mini, all right? This is the kind of thing I want to see. That's it. Don't overcomplicate it. You figure out what function you should use and what the limits are and how to do the integral. Work with your variable. Your variable, you only have one constant that's represented by a variable, which is r. And your job is to just use an analogous argument to show that the volume of a sphere is 4/3 pi r cubed. That is a mini project, counts as a quiz grade, and I forget when it's due, but I'll post that somewhere.